Okay, so an example of a situation where you got to understand something that's not automatically given by formula. You got a projectile. You know that if you're watching that projectile from some point beyond where it's going to land, it's going to look like it's going up for a while. It's going to look like it's going down for a while. Okay? And right in between, as you said, it looks like it's stationary for an instant. Okay. So, drew a picture. An attempt at a parabola. You can measure and see how well I did. Probably not very well. But you're here, and here's the path of the projectile. Where is the projectile when it looks like it stops? Now, you said at the peak. No. If you were at the same level as the peak, it would, but no. Okay? You said you can't do it from here? Well, yeah, you can. Okay. But, you know, it's okay. And then you jump to, tangent line. That's it. Okay? So you draw a tangent line from here to the curve. Hopefully you don't have to fudge too much. So let's just say that the tangent line hits right here. Okay? So, okay. So, well, how are you going to figure out just where here is? Well, let's say you've got the equation of motion. V of 0 to V naught, the same thing, okay? Let's just say that x equals 0 here, so we don't have to add any numbers to it. Okay? Measuring it from this point. Okay? Now, there are two ways we can do this. Okay? There's your R of t, V of t. Well, that's going to be no t on that, it's an I. Okay? Vy of 0 minus GTJ. And you confirm when you look at this, okay, this means that it's moving this way at a constant speed, constant velocity toward you, but it's also moving up initially with some y velocity, which hopefully is positive, it's not going down into the ground, but slowing down until it reaches 0. You can solve this if you know what Vy of 0 and Vx of 0 are. You can figure out where it is when it's at the peak, because you just set this equal to 0, gives you the time. Okay? And then you plug that in here and it gives you the position, right? That makes sense? Okay? You got to understand the mathematics of that. Okay? And you understand why this occurs, because you understand how constant acceleration gives you this, constant velocity gives you that. You have an intuition for that. Okay, so you have this. Now that's not going to help a lot in figuring out where this is, but this equation will. Okay, so now direction of motion needs to equal direction of your eye, right? Okay, well, the direction of motion is the direction of v of t. Okay? Now, having said where you are, we're going to say that this is x u, y u. Okay? M. That's Y, your I, J. Y, your I having kind of a profoundly poetic feel to it. So you have okay? So wherever your eye happens to be, that's the vector that describes that position. Okay? Now we could express that as an ordered pair also. X, U, Y, your eye, right? That's what to do with vectors. Because in a lot of cases, it's easier to see what's going on once you get used to being able to express it in terms of vectors. Okay? Okay, so what's the direction of V of t? What's the direction from R of t to Y, your I? Okay, well, the direction of V of t is the arctangent of negative gt. I'll write that in function notation. Over Vy of 0. Now we're getting into enough mathematics that it gets a little hard to connect it. But if you understand what's going on, it's just you got a rise and a run, right? And you got a direction here, okay? And that direction is the arctangent of, well, if you do a temporary set of xy coordinates here, okay, then that's going to be your y coordinate divided by your x coordinate. Well, your y coordinate is going to be how far down you got to go, your x coordinate how far over, okay? And the arctangent of that is this angle, okay? So, we have this. Now, direction from R of t to this, well, from R of t to here, okay, whatever time t, that's x u minus x of t, right? There's your I component. Whatever you write that, plus y, your I minus y of t. Okay. Okay, so that's going to be now, I just use y of t. That is y of t, right? So I'm not going to write it out over there, but I'm going to go ahead and substitute it here. just have y of t, and there's not going to give us anything to be solved, and everything else is something we can use, okay? So that's going to be minus this quantity, which gives us this, over this. So now we've got an equation. Set this equal to this and solve. And it's nothing but a simple quadratic equation. Multiply through by your denominators. You're going to get a t squared here. You got a t squared here. You got a t here. Put it all on one side. Use a quadratic formula. You can figure it out. Okay, you can solve for t. That doesn't say where the ball is, but to get where the ball is, you just plug t in here, and you got your x and y coordinates, and plug in here, and you got your r of t. So you know where that's going to be. And then the next question is, how fast do you have to run to get to here by the time the ball comes in? That's not how you catch a fly ball. That's how you might train a robot to do it. Okay? Robot waits till it's stationary. Okay? Of course, the robot doesn't know where it's going to hit. That's not going to work. Right?
Maybe the robot can at least be hit by the ball.
That'd be aversive conditioning, might work. But what the robot's got to do is look at the rate of change of the apparent velocity of the ball, which tells something about the rate of change of the tangent line, and there are many ways it can be approached. Okay? Now I'm not going to ask you to analyze that, unless you want a good project. Okay? But you see how this could be done with your vectors. Okay? Another way to do it is say, okay, well, there's my r of t. It's, you know, this times I plus this times j. But I can now eliminate t from these two equations. T equals your x squared over dx 0. And I'm not going to put the t in here just because it's confusing to see t to both sides. But this is a dynamic, x is changing with time. Okay? Then I plug it in here. And I get that for this term, and minus 1/2 g. Okay? There's a capital H. Where A is just this, because that's your coefficient of x squared. B is Vy of 0 over Vx of 0, which is the slope of the initial vector, right? V of 0 vector, okay?
Can you say again what the t was? T is x over... At the very beginning, what does t equal?
Here,
How does that work? Yeah.
solve this equation for t. Maybe I should have said that, I thought it was obvious, but I know better. Okay? So you just solve this for T, plug in here, and you get your equation. You don't have a C. You don't have a C because you judiciously chose the origin to be the initial point. Okay?
X of 0, 0.
Now, in reality, if this is a baseball game, the ball is actually hit from a little higher than here, right? Okay? But you could still let that point be the origin, and just measure yi compared to where the height at which the bat hit the ball. Okay?
And if you're in the stands, that might work anyway.
Oh yeah, yeah, be at the right height. It works no matter where you set your origin. It's just that if you set your origin someplace else, you're also going to have a y of 0. Okay. Which is going to then, okay? Well, actually it appears, yeah, I mean, that's going to be your C. So, okay? Okay, so, you can then analyze it based on the properties of this parabola, and you can figure out the equation of the tangent line of the parabola. Okay? At what point does it intersect your eye? Set where? Obviously, it intersects your eye at your eye, but at what point? On the curve. You get a tangent line that intersects your eye.
Wouldn't that be slightly after the point at which it's stopped moving? Because when it stops moving, the tangent line should be flat, like perfectly horizontal, shouldn't it?
You're confusing the point where the ball stops rising with the point at which your eye perceives it to be stationary.
All right, so they are different.
No, they're the same. The ball doesn't actually stop at this point, it's just that your eye sees it
At the apex.
as stationary.
of the tangent.
Now, if your eye is good enough to see the ball getting bigger at that point, okay? But for a baseball and a typical outfield fly, no.
So when your eye perceives it to stop moving, and whenever its vertical velocity is equal to 0 or different.
Yeah,
Okay.
yeah. Your eye sees it, when it's at its apex, it's still coming at you. Okay? At the apex, the tangent line's out here. Okay, as long as the tangent line's above your eye, and you convince yourself of that. Okay? You're not going to yet be at the point where the ball makes the transition from appearing to rise to appearing to fall. And that's the common confusion, especially if you played some baseball. You know, say, okay, it stopped, it's at the top of its arc. It's your intuition. I bet there are major league ball players that don't understand that.
Then you visually do a million calculations in your head to figure out where you need to run to.
Well,
With your
then,
depth perception,
you train yourself. It's just a training thing. You know, you start running toward it, you run too far, you say, okay. You just develop a feel for how that goes. Remember when I was training my daughter's dog, they were living in the house at the time, to catch. And I was just thinking of this the other day, because she's now 10 years old. She's at catching things. And you'd hold out a stick. Yeah, she's like a 55-pound lad. She's got a pucker in her. She doesn't look exactly like a lab, but you have to look close. And she'd take a flying leap and grab that thing violently. But if she happened to hit flesh, she would instantly ease off so it wouldn't even scratch it. So you never had to worry about getting your hand taken off. And I think she's lost those habits because she's not living in the house anymore. She's 20 minutes down the road. But, you know, hold out a treat for her, you know, one of these. Yeah, sure. And I'm not sure her senses are refined enough. She doesn't want to hurt you, but there's a stick. She doesn't necessarily pay attention. But okay, the point about that dog though is I was tossing pieces of popcorn to her. And at first she'd miss them, but then take her like she had puppies about this big, you know. And then I'd throw them a little further back, a little further aside. She adapted very quickly. I mean, of course, yeah, their brain is well wired in their bodies to catch prey. Okay? Catch anything.
Popcorn never saw it coming.
I felt sorry for the popcorn, but they took one for the team. And then I threw on a little too far. And she went back and she flipped over. Now, puppy, you know, it doesn't hurt her a bit. And maybe I got her to do that once more, never again. So I'm just saying, and our brains are pretty good at seeing positions. We're among the better animals at catching flying objects for different reasons, because we usually don't catch our prey. But we're pretty good at that. Not as good as a hunting dog, okay? Or as any dog is used to. So that goes into neuroscience. And there's some pretty good explanations out there, I think, about the pathways and so forth that you reinforce and adapt. But it's not done mathematically. So I might have said this, I used to play intramural football when I was half my age, which is still pretty old. And you know, I remember one time, I was in the open, the guy threw me a perfect pass, I was calculating that arc. I did all the calculations right, and then I forgot a negative sign, and the ball just dropped straight down 10 feet in front of me. The path just totally violated the parabolic arc because I forgot that negative sign. Actually, it was a little megalomania. That idea, because my forgetting the negative sign is not going to affect the path of the ball, right? Okay. So no more is your outfielder going to rely on calculations. And most of them don't have the mathematical background to do that anyway. Okay? I told you I learned complex variables for an NFL quarterback, right? Yeah. Made the cover Sports Illustrated half a dozen times, I think. People were fascinated. Yes, I was a championship winner. So. Yeah, Jim Brown in his backfield. Paul Warfield. I think there were 4 Hall of Famers in that team. But, and he didn't make Hall of Famers. He was a good quarterback. He could have done that, and sometimes people would accuse him of overanalyzing things. Now, I'm sure he analyzed football trajectories and stuff, but I don't think it had anything to do with the intuition that he used when he saw the receiver. He was not doing calculations. In training himself, maybe he relied on something. Okay, well, I think I was 31 years old when I had him for the course, prematurely gray. Jim Brown praised him for staying in the pocket and taking the hit. He wasn't a great big guy. I mean, he was 210. interesting guy to learn complex variables from. Okay. So, for that digression, but do you understand what I'm trying to communicate here? The things you got to know. Other situations, what if you raced a pendulum and a ball down the incline? Which one would start out faster? Well, it depends on the incline and stuff. If the ball starts out faster, is the pendulum ever going to catch it?
No.
Well, the ball automatically, okay, the ball's initial acceleration is greater. When I say it starts out faster, that was really a dumb way to say it. The ball initially goes out ahead of the pendulum, both released from rest. Okay? Pendulum ever going to catch it? Why not?
Because the ball is going to continue accelerating, but the pendulum, once it reaches its maximum velocity, it begins to deaccelerate.
Well, yeah, certainly, if it hasn't caught it by the time it gets its equilibrium position, it ain't gone. Because it starts slowing down and the ball continues. Okay? But somewhere between here and there? Could it happen? What do you know about the acceleration of the pendulum?
They'll reach the same acceleration, but they'll still have that distance between.
The acceleration of a pendulum changes.
How?
It's always towards the resting position. It's always
Yeah.
towards equilibrium.
Okay, but just between here and equilibrium, because we reduce the problem to what happens between here and equilibrium. If it doesn't happen between here and here, it's not going to happen, right?
Because
But why doesn't it happen between here and here? Or does it?
Because the pendulum's acceleration is greatest when it's first released.
Yeah. If they have the same acceleration, the pendulum's going to be loose. Now, why does the pendulum's acceleration decrease?
Because it's getting closer to the equilibrium point, it's slowing down.
It's not slowing down, it's speeding up
Well,
all the way to the equilibrium
the acceleration
point.
is growing smaller, but the velocity is
So
still.
why is the acceleration getting smaller?
Because it's proportional to the distance between the pendulum and the
Yeah,
equilibrium
because
point.
you have a linear restoring force, or a restoring force that decreases, and Newton's second law says your acceleration has a constant proportionality with the force, right? That proportionality being 1 over the mass, okay? So, yeah, that's it, okay? So, you have a question like that, okay? And you can ask other questions, okay? If you know the dimensions of the pendulum, accelerations match at some point after you started, okay? Then what does relative motion look like? Well, you can translate that into equations if you have the intuition to understand what's going on, okay? And that's an art you need to develop. You have very solid mathematical skills. Yeah, maybe you need to think a little more about factors, but I don't think I'm seeing any terrible problem with that, okay? So anyhow, expect some more problems and get the ones I've signed done. Get your labs analyzed, kind of mounting up on you. Definitely expect a midterm test before the end of the month. Okay? Okay, and really, when you talk about what we have to do, you've got a lot of the main concepts here. You just have to learn to use them. Just a few more concepts like angular energy. So you've got to understand energy here. And we haven't talked about potential energy. I was going to today, but I thought we'd just stop and see where we are. And I'll probably introduce the idea of potential energy in one of your problems. Okay, then we'll work more with it next time. I might have already done that. To some extent, I got to look back at just what I assigned last time I saw you guys. Was that last month? Was it Okay. Anyhow, that's all right. That's all right. As long as you get the problems done, the labs analyzed. Okay.